Thanks, Joseph. Yeah, thanks everyone. It's a real pleasure to have this opportunity to share this case study that me and my colleagues Rhonda Sullivan and Scott Dennett put together on sort of a real practical application of these simultaneous stochastic optimization techniques. So I'm just going to start the presentation by doing a review or high-level overview of what the traditional long-term mine planning process looks like in our iron ore business at BHP. So first, ore body models are constructed using geological inputs and metallurgical from drill holes and metallurgical inputs from metallurgical test work. Then, along with some geotechnical constraints and some financial assumptions around the metal price, some premiums for quality or different product types, and mining costs, an alternate pit is an optimal ultimate pit is defined. Obviously, that can't be all mined in one go. So there's within that optimal pit, optimal mining sequence is generated, and from that allows us to calculate some NPV values, and maybe by flexing some certain parameters, we can assumptions around costs or capacities, we can get some high case values and some low case values around that NPV. But that approach has some limitations. So a couple of the limitations that relate to the inputs to that process, that generally those processes are based on deterministic models that don't reflect the real grade and product variabilities, nor do they account for the uncertainty in our knowledge of those properties across the ore deposit. So generally those methods produce an averaged or a smoothed representation of the grades that compared to what we will actually recover at the time of mining. And you can see these images on the right here that in some areas of our ore deposits there's quite a lot of uncertainty between the realizations in our stochastic models, which we don't see when we use the traditional methods. Some other limitations now on the mine planning side of some of the methods that are used rely on the aggregation of blocks. So aggregation of blocks in the models into larger panels. They do this to reduce the size of the optimization problem. However, in doing so, it doesn't reflect the real mining selectivity at the time of mining. Another issue is around the stepwise or local optimization. So the fact that the ultimate pit is determined separately at a different stage to the definition of the mining sequence. And also, if there's multiple pits involved, those in the mining complex, they will be optimised independently of each other. The ultimate pits are independent, but the mining sequence can be generated together. So, because of those limitations, that's led us to that's the motivation for this case study that I'm going to talk about today. Where we use simultaneous stochastic optimization to address some of those issues. In our case study, it's an iron ore mining complex. We wanted to include multiple mine, like a multi-mine operation, with multiple downstream destinations. It also included stockpiling options and incorporate some ESG or environmental and social governance considerations, and simultaneously optimise that mining sequence to manage the geological risk in that mining value chain, and compare that to our traditional techniques, which is done using our internal company software called Laser. So just some details around the ore deposit models that were used as input into the simultaneous optimization. There's 2 mines. Each model each of the mines has 10 realizations. It's a rather small block size of about 10 by 10 by 4 for very large volumes. So each mine has over 6 million blocks. In the ore deposits, there are 3 main material types: so unenriched material or waste material, high phosphorus supergene, martite goethite ores, green, and low phosphorus hypogene martite microplating hematite ores in red. And for each of the ore deposit models, the head grades of each block are simulated along with the layout of the different material types and their bulk density. So iron ore is sold as different products, lump and fine products, which rely on geometallurgical models for us to understand the recoveries of those different product types. Though in these models, the metallurgical recoveries are modeled using a transfer function, given the average blades of the simulated head grades. That transfer function relies on the depth below surface, the rock type or the material type, and the quality of the ores, and the specific gravity or the density of those ores. And because those properties are simulated, the metallurgical recoveries for each block will differ from one realisation to another. This slide is just trying to give a bit of an overview of the key value driving properties in iron ore. So iron ore is the fuel rate and productivity of the smelters or the blast furnace are the key value driving properties. So iron ores are fed into the blast furnace in alternating layers of iron ore and fuel, in this case coking coal, and the quality of those iron ores, so the iron grades and the impurities drive productivity, and also the physical properties of those ores, so their size, distributions allow for greater or less transfer or energy to propagate through the column in the blast furnace, and that impacts the productivity of the blast furnace. It's also important to note that some fines products ores require some pre-processing before they can be charged into the blast furnace, whereas lump ores can be fed directly into the blast furnace, and that means that there's a premium paid for lump ores over the fine ores. So in our case study, it's a rather simple case study, similar to the base case from the previous presentation. There's 2 mines. Each mine has its own waste dump, a stockpile, and the stockpiles and the mines can send material to the crushing and ore handling facilities at the mine, from where they're blended and separated into lump and fines products. Those products are then transported over long distances to the port and sold as those separate products, lump and fines ores. But during that transportation process, there's a degradation of the lump product that happens. So we lose some of the lump product, degrades to the fine product, and that requires processing before shipping and and we don't see the quantities of that premium lump product by the time it gets to our customers. And that is modelled in the mining value chain using a transfer function between the mine and the port. Here's some details on the mining value chain itself. So in this run, we used a mine life of 10 years, maximum mine life of 10 years, a discount rate of 7% per annum. The mining complex isn't constrained by the mining equipment. So mining equipment and mining rates are not a constraint. They're not a constraint. And it's the mining complex is more constrained by the crushing capacity, which is about 20 million tonne per annum. The product specifications that the mine is trying to achieve is iron fines grade of greater than 60% iron, with a phosphorus grade of less than 0.12%, and an ultra fines content, which is the measurement of sub 150 micron material below 21%, which relates to some of these ESG considerations, but also materials handling properties through the mining value chain. There are also some scheduling constraints that are applied for the mining to ensure slope constraints honoured, accident sink rates, etc. So the optimizer, simultaneous stochastic optimizer, can modify several decision variables. So it's a two-step process or two-stage process. In the first stage, the optimizer can modify or needs to decide the period in which each block is mined and its destination, whether it goes to a waste dump, stockpile, or to the crusher. And that is done by discretizing the grades of the material mined in each period and selecting which bins go to the separate destinations. In the second step of the process, the transfer of materials between intermediate locations on the value chain is determined. So that could be materials moving from stockpiles to crusher, or the crusher through to the port. And this is done under the assumption that the mining value chain can react to the uncertainties of the incoming materials. Here's some the optimizer objective function has been configured to maximise discounted cash flow whilst minimising deviations from production targets and product quality specifications. And on the right-hand side of the slide, you can see some examples of some of the constraints that are applied. So ultra-fines content relates to materials handling properties, so it may slow down throughput through certain parts of the mining value chain, but also can impact some of the local communities around our operations through the generation of excessive dust. So for those reasons, the optimizer, we're trying to minimise the quantity of the ultra-fines material. And there's also an exclusion zone relating to a protected area that we don't want any mining to occur in. So the output from the stochastic optimization, the blaze is compared to the blazing sequence. It's done using the realizations of the simulated model, as they are more realistic of what is actually going to be encountered at the time of mining. However, the blazer inputs use the traditional deterministic models as inputs, whereas the stochastic simultaneous stochastic optimization uses stochastic inputs. And you can see some examples of the different properties for the deterministic on the right and the stochastic on the left. And here's our results. So the stochastic sequence is presented with the blue lines. You can see that the P50 is the solid line, and the min and max of the realizations or the uncertainty around that is shown with the dashed lines. You can see the stochastic optimizer outperformed the blazer sequence. They mined for 2 different periods to start off with. So the laser sequence stopped mining at the 8th year and didn't mine any further beyond that, whereas the stochastic sequence was allowed to continue mining. But at that 8th year, you can see that there's a value increase of about 13% for the stochastic sequence over the laser sequence. And that's achieved with the throughputs through so this is the crusher, the 20 million tonne per annum, slightly lower for the stochastic sequence in the laser sequence. But just looking at those last 2 years, or the last year periods 9 and 10, it would need sort of expert knowledge to understand whether those periods were actually worth mining in reality. It achieves the higher MPV if we start looking at some of the quality results, or the results for the product quality properties. We can start to see why we achieve a higher MPV using the stochastic sequence. So the iron grades are higher for the first 4 periods in the stochastic sequence than the blazer sequence, and the phosphorus grades, product grades, are maintained below the threshold of 0.12 throughout the life of the mine, whereas the blazer sequence deviates and sends higher phosphorus grades, which will incur a penalty. The shipped ultrafines contents, that relates back to the materials handling and the ESG dust constraints. So we can see that the stochastic optimizer maintains those values below the threshold of 21% throughout the life of the mine, whilst the blazer sequence exceeds that threshold for several periods, which would not be a great outcome for the communities near operations. We can see that the stochastic sequence in the image on the right maximises the quantity of lump product sold in the early years of the mine compared to the blazer sequence. As there's a premium for that, that's how it's generating that extra MPV. Here's some examples of the mining sequence generated by the 2 different methods. So you can see the blazer sequence has a lot of constraints around mining horizontal panels, and whereas the stochastic mining sequence mines more vertically throughout the deposit. You can also see that the stochastic sequence prefers mining higher risk areas in the ore deposit to later periods of the mine's life. So near the base of the ore deposit, and in this area in mine 2, there's a lot of uncertainty around the grades and the tonnages in those areas, and the stochastic optimizer has deferred them to later periods. So in conclusion, we concluded that the stochastic optimizer outperformed the blazer sequence, and it did that by maximising the value driving properties, so iron grades and the quantity of lump product, through minimising deviation from production targets and high grade zones deferred to later on in the mining sequence, high risk zones, deferred to later on in the mining sequence, and minimising exposure to materials handling and air quality risks. relating to the physical properties of the ore. But what we did find was the computational resources required to optimise such a large mining sequence was very, very high, and that any improvements in solar efficiency would be a key area for further research. Future work, we're looking to do some more complex case studies, so complex case studies that involve more complex mining value chains, so including a beneficiation circuit and potentially external ore sources, and also incorporate alternative sort of uncertainty, including metallurgical recovery models, so uncertainty in those models, and also the iron ore demand, iron ore price, demand uncertainties. That's everything.